anyway, today is about geology. This isn't my primary training. I haven't been officially schooled in geology, but I have my own interest in it over the past several years, and my own questions that I've developed over the last several years that I haven't seen anybody answer, or at least I haven't come across answers in what I've read. So I'm just presenting my own observations and questions about geology, even though my main area of training, of course, is medicine and genetics and that sort of area. So we're kind of going to explore this together, and if you have answers or additional questions, it'd be great to hear them as we go along. Oh, by the way, this is a picture of the Grand Canyon, and the geologic column, or the layers of sedimentary rock, that are all, everybody agrees, are water deposited, and they're present on every continent all over the world. There's some areas where they're patchy and they're not present, but generally speaking, they're present just about everywhere. And I show a picture of the Grand Canyon here because this is probably one of the most striking areas in the world where you can see many layers exposed in their horizontal array. And it's really striking, so that's why most people, when they start off talking about this topic, they present the Grand Canyon, and rightfully so. Features of the geologic column. Obviously, it's made of layers of sedimentary rock. What that means is originally the rock wasn't rock. It settled out from water as sediment. And then it was mud on the bottom, and then over time it dried out and then turned into rock over time. Sometimes the rock is hard, sometimes it's soft, depending on how it was cemented together over time. The interesting thing, one of the interesting things anyway about these layers is that they're generally flat and even relative to each other. Of course, earthquakes and tectonic movements have tilted and distorted them sometimes over time, but relative to each other, they're horizontally flat and very even. Their surfaces are very smooth. Of course, they're generally found all over the globe. There's some areas that are missing. They're even found on great mountains, the biggest mountains in the world, the Swiss Alps, Mount Everest, American Rockies, Himalayas, the Appalachians here of the geologic column. And they're popularly thought to represent millions and even billions of years of Earth's history, recorded in time. Here's a schematic of the geologic column. The geologic layers, of course, are rock, but they contain fossils. And the oldest layers of rock are called the Cambrian. There's also these periods or eras called Paleozoic, Mesozoic, and Cenozoic, starting from some 550 million years ago in mainstream literature, and they contain an order of life from what is commonly called simple to more complex. Start with single-celled organisms, and move up to multi-celled organisms, flowering plants, and then land animals, and all the way up to us. We'll talk about fossils tomorrow. So, if the geologic column is really old, and I'll tell you up front right now, I don't believe it is. I believe that the geologic column itself and life on this planet is young. And I would say at least less than 10,000 years. And I think I can give very good evidence that it's less than 100,000 years. I personally believe it's less than 10,000 years, probably around 6,000 years. And so we'll see who's right, or at least if there's reasonable arguments for my way off base position. So let's just assume, first of all, geologic column is old. What would you expect to see as features of the layers if it really was old? Well, let's say it got laid down, and it all got laid down flat at first, and then some weathering comes along. It gets uplifted on top of a mountain or something, and you get some weathering. The weathering is generally almost always uneven if it happens slowly over time. And so it chops up the layers like this, and then the mountain goes down. You get some more layers deposited on top, and they're flat too, and so they deposit in between all these little cracks and crevices and layer like that. And so you preserve the record of erosion, multiple erosion events, and then multiple layer events over time. That's what it seems reasonable that you'd expect to see if the geologic column was old, and it truly represented long periods of time of deposition and erosion happening over the course of tens and hundreds of millions of years. That's what it seems like I would expect. And sure enough, we see that the top surfaces, when they're exposed to erosive forces, are indeed uneven and almost a random appearance. But then you notice the layers underneath. The layers underneath don't seem like they were ever exposed to surface pressures of erosion because they're still perfectly flat. You don't have any record of previous erosion events. Only the very top layers have evidence of erosion preserved in the layer to any significant degree. You may have evidence of rivers down here somewhere, but these evidences of intra-layer erosion are usually very limited and very crisp, and don't really show evidence of long periods of erosion. And here's again the surface that we see today, but we don't see this actually preserved in the fossil record, or not in the geologic column. Here's a schematic. If you cut the Grand Canyon in half, all the way to the Grand Staircase, this is the Grand Staircase, and you can kind of see water, right? It kind of looks like a staircase. And the Grand Canyon is kind of on a dome area, like a hill, and then it's cut, this is the Grand Canyon here, and it's cut down in this sharply defined wedge cutting. But you notice something interesting about these layers, and also the surface of the Grand Canyon, they're all very smooth. The layers themselves are smooth relative to each other. No uneven erosion between them. And also the surface of the Grand Canyon is smooth. And then the staircase, interestingly, it's kind of lined up like this way, but then the edges of the staircase are sharp. They're not eroded off and have that dendritic pattern of erosion like we saw in this picture here. And just a close-up view of how sharp these layers are defined. Here's the Coconino sandstone. It's the third layer from the top right there. And then underneath of it's the Hermit Shale, and it's red. And here's the line between them. And it's very smooth. And they're separated by tens of millions of years, supposedly. And here's a crack in the Hermit Shale. So this crack right here, it's 7 meters deep, 21 feet deep crack, and it's filled with pure Coconino sandstone. But now, I mean, let's say this is the surface of the ground, 100 million years ago. Let's say that's the surface of the ground, and it stays the surface of the ground for a few million years, and then it cracks. What happened? I mean, wouldn't it get filled with some contaminant or something? Why did it get filled with pure Coconino sandstone unless this sandstone was deposited rapidly and suddenly, and kind of a catastrophic event? Here's the layer on top. You see the sandstone is kind of layered, angled like this in its orientation, and it got shaved off flatly by the layer on top. How do you shave off something that flatly slowly over time? Doesn't it require more of a rapid shave? And in order to keep it so flat. Here's just a little video that illustrates what I'm talking about.
Deposition of flood deposits from tidal action means there was a little time for erosion to occur between successive layers. On the long time scale envisioned by evolutionary theory, there should be considerable evidence found of erosion and infilling by successive geologic formations during the weathering expected over millions of years. The geological layers of the Grand Canyon are remarkable in showing little or no evidence of erosion between different layers. Instead, we see pancake layering very much consistent with the rapid deposition envisioned by the flood model. Erosion did not occur until all of the layers had been deposited.
Some people may recognize some of these names. Gentry is a common name, and Lionel Sheeple will be here this weekend. And that's just an interesting question. And to me, I haven't seen a reasonable answer why the layers are so flat all over the world, the whole world. So you basically have to imagine if these layers are so flat all over the world and there's no really significant erosion between them, was the world that flat for hundreds of millions of years? No mountains, no nothing? How did it stay that flat for that long?
They have a typical surface of...
Before he goes on, this was Professor Veit. He used to be an evolutionist, atheist, and he became convinced because of geology for him. And he's also a zoologist, so the genetics didn't hurt. But he's talking about some things that are very impressive to him. One of the interesting things about his videos and series is this particular experiment that he does with what's called turbidites. It turns out that a lot of the layers in the Grand Canyon and elsewhere in the geologic column are what are called turbidites, and they're actually mud flows. And these mud flows, the grains and the sediment are sorted, course-defined, everywhere throughout multiple layers, and they're all flat. So he describes what he thinks made these layers so flat without getting all mixed up.
Here you have a typical surface of the earth with valleys and hills and what have you. And now we're covering it with water. The underground fountains shoot out. It's pouring rain from the top. Ocean water is being poured over the land. And you have these massive, catastrophic mud flows. Let's see what happens. I'm going to create an earthquake over there. See it shaking? And the mud is going to start flowing under the water from the high ground, over hills, over valleys. There it goes. You see that? There it goes. Over the top. It actually goes over the tops and into the valleys and covers everything. And then the mud settles out. And you will see that it fills up the valley and smoothly covers the top. Now that is soft mud, yes or no? All right. Now what if there's an earthquake over there and there's an upheaval and boom, another one comes along and flows over this one? Let's see what that would do. Would it mix it all up, churn it all up? What would happen? Well, let's see. Let's do it. Here we go. Another one. Boom. There it goes. Can you see that it's swirling in the front there? Okay. Now if it's swirling and flowing over the top, do you think it's possible that there where it's flowing quite fast, that it could whip a little bit of the bottom into the top, yes or no? Okay. But then they would both have to be soft, right? Okay. Let's watch. There comes another one. Boom. Notice the swirling. Over the top. Settle down. This is great stuff. Watch it. Settles down. What do we got? 3 distinct layers. And the valleys are being filled in. That's exactly what you find in the geological column. The bottom areas, the valleys are filled in, and then they get flatter and flatter and flatter. And these are actually, by comparison here, huge on a scale. Mountains. So now we can see that the next ones will just gently flow over the top. There they go. Boom. And the next one. Boom. And we're going to go a bit closer after the last one comes. And these are all soft layers of mud that are forming. Now we're going to zoom in a little bit, go a little bit closer. Let's just stop it there. What do you see? Flat layers with what type of contact between them? Flat. Surprisingly little mixing. You agree? You would expect more mixing. Very little mixing. What else? Let's check it out. Here we go. Let's go a little bit closer and zoom in on some of these rock formations. Now these are soft mud. And there we go. And we'll stop it over there. Now it's hard to see, but if you look at this layer over here, you'll see that the heavier stuff, the pebbles, are lying at the bottom, and the softer, lighter mud is on the top. So they're graded coarse to fine.
I apologize for the quality of the video, but that's the best I could do with the equipment I had at the time. So we'll work on improving it later. But if you can get the original videos here, it's even clearer, and it's an interesting argument. And he goes on with this
bottom
layer
layer and a top layer, and some of the bottom is whipped into the top. Or here, you have a top layer pushing into the bottom layer and compressing it. So they must have both been mud when it formed. Look at that. I call this slide the Geologist's Nightmare. Here you have a layer of rock, and a layer of rock on top, and look at that. Can you see the total mixing here? This little piece is a flame, and the bottom layer has been whipped into the top. What does that tell you about the two layers? That they were both soft, and that they formed catastrophic. Now you have a low cost, there's the bottom one being pushed was soft. Look at that. That's the Alps, folded. Look at this one. This is in Africa. Absolute folding of the rock.
I mean, that's a pretty good argument. If you have a layer there for millions of years, you would think it would turn to rock by then. And how would you get it to flame up into the layers above it? How do you get this course-defined gradation if it's not formed in a catastrophic manner? Certainly it doesn't make sense that it's settled out over millions of years. Or else you wouldn't have that gradation and you wouldn't have that evidence of mixing going on. At least I can't figure out how you would do that. Also, the speed of erosion. Interesting, the Rocky Mountains are currently being uplifted. They're increasing in size, or growing actually, by between 100 and 1,000 centimeters per 1,000 years. But there's no change in absolute elevation because the erosion rate keeps up. So you have rain falling down on the top of the mountain, eroding it off, and then you've got push-up from the bottom, pushing up the mountain on top, and more erosion. So the absolute height, does that make sense? Stays the same, or just about the same. Does that make sense to everyone? Yeah. Okay. So the erosion rate matches the uplift rate, and currently the uplift is thought to have started about 70 million years ago. So let's do a little math. If you have an erosion rate of 100 centimeters per 1,000 years, that equals 1,000 meters of erosion per million years, or 70,000 meters in 70 million years. Okay? So the total thickness of the layer in this region is only 3,500 meters. Why are the layers still there? If it's really 70 million years old. Does that make any sense? If you have erosion going on at about 100 or whatever, even higher than that, 100 centimeters per 1,000 years is conservative. So that's kind of a minimum boundary for this erosion rate. So why are the layers still there on the Rockies? And they are. Mount Everest is another similar problem. Its uplift is thought when India crashed into the Asian continent. It started the Himalayas going, and Mount Everest about that same time, some 50 million years ago. It was once covered with 6,000 meters of sedimentary rock. It's now only covered with 3,000 meters of sedimentary rock. And the current erosion rate is actually upwards of 450 centimeters per 1,000 years. But the overall average in the Himalayan region, even on the low-lying hills, if you take everything into account, it's about 200 centimeters per 1,000 years. So let's just take a minimum, like 100 again, centimeters per 1,000 years. And what happens over 50 million years? That's 50,000 vertical meters of erosion in 50 million years. So why is the sediment still there? This one scientist, Ruataka Saki, suggested that half of Mount Everest slid off catastrophically 20 million years ago. Well, that explains some, that's some catastrophe there. But it doesn't explain why the 3,000 meters of sediment is still there, because at 20 million years of erosion is still about, it's a little less than half of the 50,000 meters, but it's still well more than 3,000 meters that you would expect to be completely washed away. Why is it still there? A common argument I hear is that, the reason why the continents aren't completely eroded away is because the continents are lighter than the underlying magma and stuff and the Earth's crust. And so they float. And so you take stuff off the top, and then they float up higher, and you don't lose your continent. But that doesn't explain how the layers are preserved. These sedimentary layers should be all washed off, and we should be left with volcanic rock, right? And at the very least, metamorphic rock. But we're not. We still have these ancient sedimentary layers that somehow avoid getting washed off. They're very resistant to erosion. That seems to be wiping them out at a rapid rate right now. The whole continent argument, let's just go through that because it's kind of interesting. Today's continents average almost a kilometer above sea level. The total surface area of the Earth is about 150 million square kilometers. So that turns out to be, if you convert it, cubic kilometers above sea level is 130 million cubic kilometers above sea level that we have in the world today. So if you have an average of I took an average of several references to determine the average amount of sediment that's taken off the continental shelves and put into the ocean per year. And it turns out that that's about 13.6 cubic kilometers of solid materials carried by the rivers into the oceans, which is equivalent to 31 million metric tons per year. So if you take the average specific gravity of sandstone, you can do the calculation. The time needed to erode all the land above the sea level into the oceans to make it all flat and at sea level is only 9.5 million years. So why are the continents still here, much less the sedimentary layers, if the layers themselves have been exposed for hundreds of millions of years in some places? And this isn't just me. Other people know about this. It's just that it's not in general textbooks. Dott and Batten are fairly well-known geologists. I mean, they posed this question back in 1971, and to me, I still haven't seen an answer for it. They write, North America is being denuded or eroded at a rate that could level it in a mere 10 million years, or to put it another way, at the same rate, 10 North Americas could have been eroded since the Middle Cretaceous 100 million years ago. So, and they're asking the question, and they don't know the answer either. Twindle recognized this problem. He published in 1976 in the American Journal of Science, so this is a mainstream journal. He writes, even if it is accepted that estimates of the contemporary rate of degradation of land surfaces are several orders too high, an order is 10 times. So several orders would be 100,000 times too high. You're way off in your estimate of your erosion rates. To provide an accurate yardstick of erosion in the geologic past, there has surely been ample time for the very ancient features preserved in the present landscape to have been eradicated several times over. The survival of these paleoforms, or land surfaces, is in some degree an embarrassment to all the commonly accepted models of landscape development. So does he know the answer? He doesn't either, and it's not like a little problem. You can be off by orders of magnitude in your estimate of erosion rates and still be right. Sparks, same thing, geomorphology. He writes, some of these rates of erosion are obviously staggering. The Yellow River, over in China, could peneplane or flatten out an area with the average height of Mount Everest in just 10 million years. The student has 2 courses open to him: to accept the long extrapolation of short-term denudation or erosion figures and doubt the reality of the erosion surfaces, or the ages, the stated ages, or to accept the erosion surfaces and be skeptical about the validity of long extrapolations of present erosion rates. So which are you more skeptical about? The current erosion rates extrapolated into the past, or the current thoughts on ages extrapolated into the past? You can't have it both ways. One of them is wrong. What about the human impact? That's an argument. Well, humans came along, a few 100,000 years ago, and we sped up the erosion rate dramatically, right? Well, that could have happened. Let's look at that argument. James Savitsky, he writes, humans have simultaneously increased the sediment transport by global rivers through soil erosion by 0.6 to 2.3 billion metric tons per year. That's not much of a percentage when you're considering 31 billion metric tons per year. So it's not really like an order of magnitude, not even one order of magnitude difference. And yet, it's not even really a problem at that, because although we've increased the erosion rate, we've also built dams and prevented the sediment from actually reaching the oceans. So we've actually overall decreased the actual sediment transport to the ocean. Also, let's just look at the Grand Staircase again for a minute, and also the smoothness of the Grand Canyon dome, and see if we can explain that as a long-term erosion process. Look how see the Grand Staircase way off in the distance? Oh, wow. Over there? Yeah. Let me show you. Now, these layers, see the layers here? Yeah. They once used to stretch all the way across the Grand Canyon, and they got washed away. Slowly, over millions and millions and millions of years. They got washed away, and they no longer cover the Grand Canyon, and then they formed the staircase. And look how smoothly they got washed away. I mean, the surface of I was arguing and asking somebody to explain this to me and talk origins, and they're saying because the reason why this is so smooth is because the layer up here, the cave bed limestone, is hard. It's a very hard sedimentary rock, and so everything else was soft on top of it. It got eroded away, and then you couldn't penetrate this, and so that's why it's flat. Okay? So the Grand Staircase was resistant, evidently. Why? So let's look at some other areas where it's flat. See, those all look kind of like the Grand Canyon there too, and there's a sharp edge here and a river going by. It's similar, doesn't it? And oh man, that's Seabird right here. And here we have the grand staircase. See that? Did that take millions of years to develop that smooth surface? It seems like it's easier to explain these surfaces, these smooth surfaces, and this linear orientation and a flat top like this by catastrophic sheet flooding. Like this was a kind of a wide flood stream coming through here, and it just kind of eroded right down through. And then before it could get everything, what happened to the water? It was gone. And what's also interesting is that we have areas around the Grand Canyon that are close to it, like Red Butte, that are evidently very resistant to erosion. All the layers around them, here this layer used to go all the way over here, all the layers for miles and miles around, they got washed away, and Red Butte sat there for millions of years resistant to erosion. Now how do you explain that? Here's Red Butte, see, all the way around it, nothing, it's flat. There's Red Butte, see, wide distance all the way around, got washed away, and Red Butte says, it doesn't rain here, or something. Here's Beartooth Butte, another very resistant butte. These layers here match these layers down here. And see how the Precambrian got pushed up, and it shoved this Red Butte up here, and then all the layers around it got washed away, and where did they go? Well, it's interesting that these layers here are warped. See how they're warped up with the uplift here? But these layers here are not warped. So what does that tell you about the formation time period of these versus these? These got warped by the uplift maybe of this, and then when this uplifted, let's just say there was flood for argument's sake, and there was all the water here, all the water rushed off really quick, and before it could get Beartooth Butte, it was gone. And what happened to all the sediment the water was carrying that it washed away? It formed these layers, which by the time it was all uplifted, there was no more uplift, and these layers didn't get warped. That's my little humble theory, but I haven't heard anything else that makes more sense to me. And here's Beartooth Butte. You see, it also has a bunch of sharp teeth in it and everything, so you know it's from those bottom layers. With nothing around it, it's just a very resistant little butte. What about these little sinkholes? These are sinkholes in the Permian cave bed, the same limestone on top of covers the top of Grand Canyon. And we've got these sinkholes everywhere, and these rivers that kind of have blind ends on them, and a smooth surface. So where else do we see sinkholes? Well, we see St. Beach, Trinidad Beach. Next to the same spot I took that previous picture, there's these sinkholes right there. See, sinkholes, so when the water goes down, it undermines the sediment and makes sinkholes. We also see sinkholes beside the Dead Sea, because the Dead Sea is shrinking these days. The water's going down, it undermines the sediment underneath, and since the sediment is mud, it's not rock, the sinkholes form. And you get that because it's mud, and it gets undermined easily. You also get these very crisp lines, see the sharp line and a blind canyon, like this that's flat everywhere else, and there's no lead up to it, it's just a blind end canyon like that, and very sharp and deep. Where else do we see that? Well, anybody ever been to Washington State, seen the Scablands and Dry Falls? These are famous areas in Washington State. Harlan Bretz, anybody heard his name before? He proposed that these features were the result of a massive flood. And he proposed that in the 1920s, and he was scoffed at for 80 years. And then eventually he was proved right, because they decided it wasn't Noah's flood, so maybe he could be right. It was a flood that developed behind the glacier in Canada, and when the glacier got undermined, this massive 2,000-foot wall of water came rushing through and created the Scablands. And these giant blind end canyons. Here's Dry Falls here, you can see the layer. This is the blind end canyon. And he won the Penrose Medal for that. So you can have floods, you can have massive catastrophes that affected 2/3 of Washington State. You just can't make it Noah's flood. Here's the Grand Canyon from space.
Question.
Yes.
I just, for one, the water couldn't melt that fast enough to get that amount of water.
It was an ice dam. The lake itself, Lake Missoula, was a giant lake, and it undermined the dam.
Okay.
Here's the Grand Canyon from space. You can see that this right here is the Grand Canyon, that little line here. And you see here, this other canyon, that's the Grand Staircase. It comes back. Does it look kind of like a giant blind end canyon to you? So which is the Grand Canyon really? Let's take a closer look. Here's that little tip area on there. Whoops. You can see that the staircase coming. That's the Grand Canyon, right? If you step back a little bit though, which is the real Grand Canyon? This one, right? Looks to me like it should be the Grander Canyon. And so here you start out with a straight shot. The river's going pretty straight, but then it starts going more curly over here in the western part. And there's a V shape of the big canyon, the Grander Canyon, if you want to do it that way. And here you see this huge cliff face this way. So what I propose is, see this sharp line here? Is that this used to be a huge lake, and it broke through right here, released a ton of water all of a sudden, and it carved out this cliff. It eroded back like this in a sharp line, and then eroded back that U-shaped blind canyon, just like it did in the Washington State, the Dry Falls, just on a massive scale, massive scale. And before it could go back farther, all the water ran out, and the rest of the water created the tiny little Grand Canyon. And then, the water's going really fast at first, and so it's just sort of a straight shot. And as the water runs out of energy, it starts to form these hairpin turns as it goes along. That's the night here. Younger with time, I went to one of my professors at Loma Linda, and I asked him, you believe in evolution, that the Earth is millions and millions of years old, at least the life on Earth and stuff. I was like, what's the number one evidence that convinced you that life on Earth is millions of years old? He's like, well, the number one thing for me was the lava dams in the Grand Canyon. These volcanoes erupted after the Grand Canyon was formed, already a canyon, and the lava flowed into the Grand Canyon and built lava dams. And as the lava dams were built, the water behind it from the Colorado River got backed up and made this giant lake, and then the lava dams had to be eroded over time in order to get the river to go again. And for many years, for 50-some years, it was thought that it took hundreds of thousands of years, or at least 100,000 years, to erode each one of those lava dams, and there's many of them. There's many lava dams in the Grand Canyon. And so I was like, well, that's a tough one. That's a tough argument. And so I was like, well, I'll go check it out. I'll go check into it, and I'll come back and tell you what I found. And it turns out that very same month that I had this discussion with my professor, is that the University of Arizona, I was like, well, where should I start looking first for information about this? I was like, well, where's the Grand Canyon? Mm-hmm. So I went to the University of Arizona, to their website, and they had just published that same month a research by two individuals who had gone to the Grand Canyon and done tests on this, and they found exponential decay curves on the side of the Grand Canyon where water had made these rapid declines that you usually see with massive dam breaks. And they, based on the estimate of these decay curves on the side of the Grand Canyon wall, they estimated that these lava dams each collapsed within 80 minutes once they started failing. The water built up behind them for a few years, and then they failed within 80 minutes. And the same thing happened in the Grand Tetons. It was a man-made dam, and they had the same sort of exponential decay curves along the side. So I went back to my professor, and I was like, look, these dams didn't erode over hundreds of thousands of years. They collapsed within 80 minutes, according to this month, this research that he didn't want to talk about. There's more pictures of the lava dams. Ed Stiles, they published this in Arizona News. 2,000-foot wall of water came through. Lava dams collapsed within 80 minutes. It released all at one time 37 times the flow of the Mississippi River during flood season. Wow. And so what does that mean as far as erosion rates for the Grand Canyon? It means that you have to reduce the age of the Grand Canyon, because all of a sudden massive amounts of water going through will dramatically increase erosion rates, markedly. So it used to be that the Grand Canyon was 70 million years old. And that was from the early 1920s until the last 5 years or so. And then they lowered the age to 600,000 years. Now that's an order, first to 5 million years, that lasted for about 20 years or so. And then they lowered it 5 years ago to 600,000 years. And then in 2007, they did another range, potassium and argon dating, and they lowered it again between different probability peaks, 600,000 years, 500, all the way down to 100,000 years. Now, how accurate can you be? You started out at 70 million years. The 5 million years was based on potassium-argon dating. This is argon-argon dating. So what does that tell you about the dating? How reliable is it, really? The same thing happened in Mather Gorge and Holtwood Gorge in Pennsylvania. These gorges used to be thought to be upwards of 180 million years old. Then they decided to do a different dating technique using beryllium-10, and they reduced the age to 13,000 years. That's 4 orders of magnitude. You're off by 10,000-fold in your original estimate of age. So that really builds confidence, in your ability to figure these things out. Monument Valley. These monuments are also very resistant. These are sedimentary layers. You can see the horizontal layering. And between all these monuments, there used to be sediment, rock, or layers anyway. And it's gone now, but somehow, see those really thin little monuments? They're very resistant. It didn't rain on them. Look, they're lined up linearly, too. There's a longitudinal monument and longitudinal here. And here they're all lined up in a row. How did these monuments decide, well, in this particular little row, we're not going to get rained on? Rather, it seems more like a sheet of water came through there, a massive sheet of water, and that's why they're lined up like that. Because the water washed through there and the water diverged around this little area, and it didn't get these monuments before it went away. See how they're lined up? They're all lined up?
Sure.
Monument Valley from a little bit of altitude there. And also, let me go back one more thing. See that long straight line there? How do you make something like that and something like this slowly? How do you erode that slowly over time?
A dunga is a rapid washout after a rainstorm. And look what you see. This whole area over here is a rapid erosion after a rainstorm. And there you have a little hill, and there you have another little hill, and flat area in between, and another one, and another one, and another one. Does it look like Monument Valley in a small scale, yes or no? That is up the scale. Make it a massive flood, and you can explain what you can see. Here's a little donga as well. You can see it. Rapid washout, and it's V-shaped, so it happened quickly. There's another one. It's also happened in just 1 or 2 rainstorms. There they are. And it happens rapidly. You don't need millions of years. All right. I'm going to take you to one of the most fascinating places on this planet. This is what is called Stadtsaal, Town Hall. And the reason why they call it Town Hall is because the whole mountain is standing on pillars. A whole mountain standing on pillars. Unbelievable. You can see right through the bottom of the mountain over there. Can you see that? Let me take you a little bit closer. Look at that. Isn't that magnificent? The whole mountain is standing on pillars. You can walk underneath it, you can walk through it, and you can marvel and say, now, how did this come into existence? How come the mountain is standing on pillars? Here you have also one of these cracks in the ground that forms after a rapid rainstorm. In that same area where the mountain is standing on pillars, you have this. Look at this rock. There it stands, a huge boulder standing on a narrow neck. And everything else in between is gone. And let me give you a scenario. Here you have this mountain forming, and the flood waters cover the earth. And the water rushes off the mountain slope. And the water gets shallower. And it rushes past this rock over here. And as the water lowers and rushes faster and faster, it washes out the bottom. But before the whole thing collapses, the water is what? Gone.
I know. Makes sense to me. Yeah. I mean, it's a decent argument. Here's that beach again. Trinidad Beach. This is a really cool beach. See, the water goes right underneath, and before the thing can collapse, the water rushes off after the tide comes out, and then he's left with these same thing that he just told, Town Hall, right, in a miniature scale. Same thing with Arches National Park. 100 million years of erosion in southeastern Utah. Or is this a rapid? See the linear lines? And then this thing just survives there. How do you make an arch like that over millions of years of erosion? See how the lines, this is horizontal orientation, everything got washed away around it, and it survived erosion in that delicate condition, while everything else got washed away. This is the story of how these arches are formed. More than 2,000 arches are there within 73,000 acres of southeastern Utah. They were once buried under almost a mile of sediment, that's true. There's local uplift, which caused cracks to form about 100 million years ago. Subsequent erosion expanded the cracks, expanded, until you form these little arches. That's the story. The problem is how do you do that slowly? That slowly. Here's these delicate little arches. See that little thing right there? That's a delicate arch. And you wash everything else around it, that slowly, and it stays up. These little delicate fins, look, they're like razor blades. Delicate fins, and you got steep erosion here, and then all the way around it, it got completely washed away, and this little delicate fin survives. And this little thing, in the middle of nowhere, look all the way around it to 20 miles away, all that sediment got washed away, and that little rocks and those little things just sat there fine. All right, move on to paraconformities. Paraconformities are also very interesting. This is the red wall limestone in the Grand Canyon, and this is the Cambrian marl underneath. What's interesting about them is between this white layer and that red layer, this white layer and red layer, there's supposed to be a 200 million year gap in sediment that's not there, that's missing. So it was either not deposited or washed away. Now what's weird about this especially is that you see these little lines down here? Those are red wall limestone. See the lines here? And the real white? They got interdigitated. How do you interdigitate something where this got deposited 200 million years before this even started, and then they got interdigitated?
What's interdigitated?
Putting their fingers together like that. See the fingers of the red wall limestone? And all mixed together. How did that happen if there's this 200 million year gap? So just for illustration purposes, because I put this together, see that's the red wall limestone, the Mississippian layer. All these layers here down to the Cambrian, gone, they're not there. The Cambrian is right underneath the Mississippian, and they're interdigitated. How do you do that flatly, interdigitatedly, and over millions of years of time? Newell, 1984 issue of Princeton University Press, made the following interesting and revealing comment concerning paraconformities. He writes, a puzzling characteristic of the earthworm boundaries of many other major biostratigraphic boundaries, in other words, boundaries between different types of fossil groups, is the general lack of physical evidence of subaerial exposure or erosion. Traces of deep leaching, scouring, channeling, residual gravels tend to be lacking. Even where there are underlying rocks that are churty or soft limestone, in other words, they're not hard. These boundaries are paraconformities. They are usually identifiable only by paleontological evidence or fossil evidence. In other words, because the right fossils are in this layer, we know it must be Cambrian or Precambrian or Mississippian or whatever. Otherwise, they wouldn't be able to tell because the layers are so flat and so nicely layered on top of each other. There's no evidence that they will ever form the surface of the ground or the ocean or whatever. In an earlier paper, he wrote, a remarkable aspect of paraconformities in limestone sequences is general lack of evidence of leaching of the undersurface. Residual sods and karst surfaces or irregular erosion channels that might be expected to result from long subaerial exposure are lacking or unrecognized. The origin of paraconformities is uncertain, and I certainly do not have a simple solution to the problem. I haven't seen anybody else come up with a simple solution to the problem, or even a good complex solution. Here's angular unconformity. See the angular layers here? Yeah. And then they got chopped off flat. How do you chop off an angle? You tilt up a mountain on the side, and then you chop it off flat slowly. How do you chop off something slowly like that and make a flat layer on top? Plastic dikes are an interesting problem too. Here are these pillars of sediment from underneath that got squirted up through layers over the top, and then the layers over the top, since they were softer than this sediment, they got eroded away and this was maintained. My question is, see, here's the Triassic, Jurassic boundary, the Cretaceous boundary here, and we've got layers that are millions of years older than each other, squirting up over into upper layers, like toothpaste. My question is after a million years or so, you expect it to turn to rock already. how do you squirt rock like toothpaste? You squirt it, and some of these tubes are filled with sand in the middle. The outer layer is clay, and then in the middle is sand from a sandy layer that is squirted up with it. And how do you do that if those layers weren't already soft and mud? My idea is that all these layers got laid down really relatively there. They're still soft and muddy, and it's kind of gooey or whatever. They're not very resistant to any sort of physical pressure. But you got all this tremendous amount of weight on a lower muddy layer. And all of a sudden, so much weight, that muddy layer is going to find a little defect in the layers above it, and it's going to squirt. It's going to squirt up all of a sudden in a catastrophic manner before it turns into rock. That's my theory. Anyway, barbs. See, barbs are supposed to be laid down once every year in lake beds, and sometimes estuaries and things like that next to the ocean. But you can count the layers, 1, 2, like tree rings, right? And here we got a leaf that's sticking up to about 7 layers or so, and it survived somehow for some years because it's very resilient leaf. And here you can count the layers, and then here you see it got folded over. These layers got folded over and kind of disrupted. There's also an interesting question. If barbs are in an area where there's any sort of life at all, like worms or snails or clams or anything that digs into sediment, they don't survive very long unless they get formed rapidly and deeply. Otherwise, they get mixed up and you can't see them anymore. Lambert and, I don't know how to say this name, Asai, measured barbs in the Lake Wallacea, Switzerland, and found up to 5 deposited per year when they did it in real time, measured it in real time. Then they did another experiment from 1811, which had a clear marker because there was a canal built in that year, until 1971, a period of 160 years. They found 360, or between 300 and 360, instead of the expected 160. So the conclusion, our investigation supported de Grier's first contention that sediment-laden floodwaters could generate turbidity overflows to deposit barbs. But threw doubt on the second interpretation that barbs or barb-like sediments are necessarily annual. They're not annual markers. They can be formed catastrophically. Even within a single flooding event, you can form many barbs. Continental drift. Pangea. All the continents used to form one continent by the name of Pangea. And Pangea supposedly split apart 200 million years ago until formed the continents we have today. So, and it kind of makes sense because the continents sort of fit together like a puzzle. If you go to a globe and you look at the globe, and you can kind of see, especially South America and Africa, they fit together pretty good. Yeah. You say, yeah, they probably did fit together like a puzzle. My question on this is 200 million years of erosion on the coastlines. You know how rapid the coastline erosion is for the eastern coast here in the Carolinas? It's, I'll get to that in a minute, but it's over some places over several meters a year. In California, it's about the same, at least over a meter on average. That's true throughout the whole world. Let's just say it was only 1 centimeter of erosion per year on average around the world, or deposition from deltas, from rivers or whatever. Would the continents still fit? After 200 million years, 1 centimeter of erosion is 2,000 kilometers of erosion on all sides. You'd only have a little dot in the middle left in the United States. And it certainly wouldn't fit like a puzzle after that amount of time. At least I can't figure out how. Also with the deposition of deltas growing like they are. 200 years ago, Ephesus, just to illustrate my point, 2,000 years ago, Ephesus was a seaport city. Now it's 5 miles inland. There's been a lot of deposition to change the edge of the coastal city. Louisiana is being lost at coastline is being lost at 25 square miles per year. U.S. spends $500 million to prevent erosion on the east and west coast. Florida spends $8 million a year alone to prevent erosion. Over the past 50 years, Washington State has lost over 300 meters of certain of its coastlines in just 50 years. Northern and central regions of California eroded about 30 centimeters per year, and some areas erode up to 1.5 meters per year. So that's pretty significant. What's the minimum erosion you can tolerate and still have the continents fit together after 200 million years? Here's Trinidad again, Trinidad Beach. you can see the erosion has really progressed inward rapidly in Trinidad Beach. Here's Texas is losing about 0.3 to 15 meters of coastline per year, depending on the location. Major Gulf Coast storms can cause, if you have a storm, it just exponentially increases the erosion rate, 30 to 40 meters of erosion in a single day. Landmark houses like at the lighthouse on Cape Hatteras, North Carolina here, it was built 15 meters inland in 1869. It had to be moved another 1,000 meters inland to avoid collapse into the ocean a few years ago. Let's see, June 2000. And because the erosion rate here in North Carolina is about 10 meters of erosion per year. This is a problem all over the world. Japan is spending billions of dollars to prevent erosion because it doesn't have much blood. So, what's the explanation for that? Another interesting thing, at the current rate of deposition of the Mississippi River Delta, the Gulf of Mexico, the entire Gulf, all the way down to the Yucatan, would be completely filled up to sea level with sediment in 10 million years. Just the current deposition rates of that one river alone. The entire Mediterranean would be filled in 10 million years by the Nile alone. Before I get into this, this is very paleocurrents. He'll explain a little bit. The paleocurrents are marks in the rocks that show the direction of flow of water. And you can still see that on the surfaces of these sedimentary layers. You can see which way the water was flowing when it deposited the sediment. And so this is a very interesting argument. Arthur Chadwick, he's a PhD, he's done research on paleocurrents around the world. And if there ever is a nail in the coffin, this is a very interesting argument.
Paleocurrents as tools. Now, what are paleocurrents? This is fascinating stuff. A paleocurrents are flow directions derived from features of sedimentary rock that reveal the direction or sense of the current of wind or water that deposited the sediment. All sedimentary rocks contain paleocurrent indicators, some which can be read and interpreted. So now if you go and look at the various layers of rock, some of it is exposed because the top layer is cracked off, and you can see, well, in which way did the water flow over this layer of rock. Science says that each one of those layers was once the surface of the Earth. Let's have a look at them individually all over the world and see in which way the water flowed, supposedly, during that time. That would be interesting. So what do we know? The results are there of some million measurements in the database. That's pretty much. Now, if you have a continent has basins, and a continent has areas where water flows in a particular direction towards the ocean. So in the United States of America, for example, there are these basins, and the water will flow from all the directions into the basins. Plus, there will be flow directions out towards the ocean. And that is a typical modern scenario. So, if we have a look at the general appearance today, here on the one side, the water will be flowing, generally speaking, towards the coast. There will be basins in the center, basins where water flows from all directions into the basins, and then you'll have flow directions to the oceans, etc., on the other side. And then you're going to have, between all of them, you're going to have rivers flowing towards the ocean. That's a typical modern world. And that's what any world should have looked like if the conditions were roughly similar in the past. Is that correct? Okay. Do we have that? The answer is no. If we go to the Paleozoic, that's at the bottom, the lowest layer, we find this very interesting phenomenon. Instead of having basins, there are none. From all the measurements that have been made, it appears that the water flowed in this direction. In other words, generally speaking, from the one side here, from the east coast, generally to the southwest, right across the continent. If you go to the next layer, the Mesozoic, what do you find? Total reverse. Suddenly, things are going in the opposite direction. If you look at the somewhat higher layers, the tertiary, we seem to find somewhat different patterns, some going this way, some going that way, some going this way. So there seems to be some form of restoration taking place. A little bit higher, we seem to have some going this way, some going that way, others going that way, and still higher, we seem to have some reversals. So what do we find? Summary. Precambrian. North America paleocurrents are variable across the craton, show no distinctive continent-wide band. So right down at the bottom, it's the same as what you would expect today. And maybe the Precambrian was once the surface of the Earth. That's consistent. The Paleozoic, suddenly you show patterns that are continent-wide and typically flow towards the west and southwest across the continent. That's impossible. You cannot have water flowing from one side of the United States all the way across to the other side, and Canada and everything else. And then in the next time, all the way in the opposite direction. And the Mesozoic, exactly the opposite. It goes from the west to the east, and then in the Cenozoic, there seems to be some continued pattern of the Cretaceous Paleozoic that become variable, so they start becoming normal again. So what happened here in the Paleozoic and Mesozoic is inexplicable. These trends are not expected in the standard model of geology. The trends reveal processes that were much larger than anything that you see today, and they are consistent with the global flood. Let's go to South America. What would you expect in the Cambrian and in the Paleozoic? Precambrian, you have basins, you have all these strange things, not many measurements around. If you go a little bit higher, suddenly, boom, the water flow right across the continent. Can it do that today? No. What happens here today? What's that? A huge mountain range. There's no way that the water can flow from one side right across to the other side, exactly as in North America. Wow! Water flowed right across North and South America in one direction in the Paleozoic. And in the Mesozoic, exactly in the opposite direction. Is this possible? No. Only with the universal flood would this be possible. If you come up higher, then you start getting variability again, as you would expect. So summary, you read it through, exactly the same pattern as you have in North America. This is unbelievable. If you put all the continents together, you have a universal pattern. So the sediments seem to have come here from the center, and the flow directions were universal. So this is an amazing story which seems to tell us that there was a universal flood after all.
I mean, that to me is very interesting. It hasn't been published yet. You have so many data points, it's hard to publish something so large, and he's working on it. But at least it's worth exploring. Some things are too amazing to be true, and they deserve further investigation. But if true, it certainly would be a huge problem to solve for mainstream geology. Because how do you have such a flat place over millions and millions of years, where currents all over the globe go in the same direction and then reverse themselves all over the globe at the same time? The only way I can possibly envision such a scenario, if true, would be if you have, let's say you have a very watery place, the world's a very watery place. There were no great mountains before the flood, there were only kind of rolling hills. And let's say a tremendous amount of energy is released on the planet all of a sudden, let's say from a giant asteroid hit, which there's a lot of evidence for massive asteroid hits in the geologic record. Let's say one of these really big ones pounded the planet all of a sudden and shook it like a bowl of jello. What's going to happen to all that water? Have you ever been in the bathtub as a little kid and rocked back and forth? And if there's no great mountains to stop the water, you got a huge tidal wave, 2,000 to 3,000 feet tall, traveling at supersonic speeds. It's going to go around and around the globe, and what's going to stop it? There's no mountains, right? It's going to go around and around. And so, also, if you got a huge wall of water and it goes around and then it leaves the spot for a minute, what happens after a huge tide? It's going to be dry for a minute, right? So you're going to get all the little animals running around, leave their footprints in this mud and sediment. just like we have in the Coconino sandstone. I'll talk about that tomorrow. But it makes much more sense. And every time it goes around, it lays down another layer. And if it got hit by another asteroid somewhere else, it may reverse and go the other direction. And at least it has the potential of making sense. And there's a lot of things that don't make sense to me in the geologic record. If you come from a perspective of old Earth, at least old geologic column. So, anybody have any questions? Yes?
What have you learned from the eruption at Mount St. Helens? Do you think that would be a good study place?
Yeah, a lot of people refer to Mount St. Helens that erupted, when was it, 80-something?
1980.
1980.
Day my wife graduated.
Right, vivid memory. So, yes, a lot of people refer to Mount St. Helens because when it erupted, it formed canyons, not nearly as big as Grand Canyon, but relatively decent canyons, and it formed them within days. And it has the layers there, the sedimentary layers, and it also deposited thousands of trees in Spirit Lake. And these trees sank in vertical orientation. They didn't sink horizontally. Just like we see in Yellowstone, we see Yellowstone National Park has this ridge where all these trees are stacked up on top of each other in forests because they're in the position of growth. But we know that trees sink in the vertical orientation because of Mount St. Helens. And so there's a lot of features of Mount St. Helens that are helpful, I think. Anybody else?
Your comment about asteroids, are you trying to suggest that as a way that a non-believer in the flood would harmonize that data, or are you suggesting that may have been involved in the fountains of the deep breaking up?
Yeah, I mean, I don't know absolutely for sure, but we do know that asteroid impacts are present throughout the geologic column. I mean, big, huge ones. Sometimes they cover significant portions of continents. The little one we have out in Arizona is just tiny in comparison. The entire, a third of the Gulf of Mexico and the Yucatan Peninsula is an asteroid impact crater. So, I mean, we have some very huge ones, and I wouldn't put it beyond question. In fact, I think it's likely that asteroids contributed to the breaking up of the Great Deep that's described in Genesis and the fracturing of the continents. I think North America and South America and Africa probably fractured very rapidly. Maybe not exactly at the time of the flood. I think there were many catastrophes after the flood that were major because in Genesis it says in the time of Peleg, the earth was divided. Right? That was after the flood. And it doesn't go into great detail, but it seems like it was a catastrophic enough event to record in the Bible. And so I don't believe necessarily in one. I do believe in a universal flood, but I don't think that's the only catastrophe that resulted from that event. Maybe subsequent sedimentary layers are part of that. Yes, sir.
Do you have any evidence that the depth of cosmic dust is an indication of the age of the Earth and stuff like that?
The cosmic dust argument, they used to think, that's an argument for the age of the solar system, as far as I've heard it mostly. They used to think before NASA went to the moon that there was enough dust that should have settled over the 4 billion years of the formation of the Earth-Moon complex to make several meters of dust on the moon. And the second words of Neil Armstrong when he stepped on the moon were, it's solid. And you don't really hear that because there's only a few centimeters of dust on the moon. And so it's far less than would have been predicted by cosmology. But I try not to go off on those arguments very much because my argument is I try to focus on the life on Earth is young. I don't try to argue for the age of the solar system or even the age of the material of the Earth because I think that's a much more difficult argument, personally. I think there's much more evidence to establish that at least the geologic column and the fossil record is young. But it's an interesting argument, I have no doubt.
Where did all this dirt, dust, sediment, where did it go?
Where did it come from, you mean? Or where did it wash to, like out of the Grand Canyon? That's an interesting thing because there's no delta, right? You would think all that dirt from the Grand Canyon, it should have made a delta if it was washed out over millions and millions of years. But there's no big delta that contains all that sediment, so no one really can explain that. It's much more consistent to me with a catastrophic, massive washout because if you have something flowing really fast, you can deposit it way out into the ocean over a wide fanned area, and you're not going to see it as a big delta. And so I think that's all the deltas that we do have, that we can identify as deltas on the whole planet, are all less than 5,000 years old, based on current deposition rates of those deltas, like the Nile, the Mississippi, the Amazon. All those cones are less than 5,000 years old, which I think is another interesting one. Yes, ma'am.
You had brought up Pangea earlier in the lecture. So are you saying that because of current erosion rates that there could not have been a Pangea? Or are you just saying that?
No, I believe in Pangea, or some form of it, because or even the Bible says that before the flood there were no great oceans, really. It doesn't talk about them anyway. It talks about great rivers. Four great rivers that watered the earth, and the earth was watered by dew, not rain. It didn't rain before the flood. And so I do believe in a massive landmass that was broken up by the flood, but I just don't believe it was broken up 200 million years ago.
It's a common argument that the layers are flat because the layers on top of them, all the weight pushed them down and made them flatter. How do you answer that?
That's kind of a funny one. I do hear that on occasion, that the layers on top of the lower layers were so heavy they smushed the lower layers flat. That's why the lower layers are flat. There's several problems with this. One problem is that if you have missing portions of a lower layer, squishing it flat is not going to fill in the blanks. Another problem is that there's fossils in the lower layers that if they were squished flat and stretched out, the fossils will be squished and stretched out, and they're not. There's also the lower layers, if they're squished that hard, they would get very hot and they would turn into glass. And a lot of the lower layers, even in the Grand Canyon, they're still soft and shirty limestones. And there's lots of other problems with that. And actually, I don't hear that from geologists very much. I hear that from lay people mostly when I discuss on erosion as well. Anybody else?
I'd like to go back to Pangea again. If all the continents were together, you'd have an enormous ocean. Or you'd have to have a different size Earth. But how do you fit all that together?
Well, I don't think that all the land surfaces that we have now were necessarily the surfaces before the flood. I think a lot of areas are sunk or not exposed that were before the flood. So I don't necessarily think what's present now has any resemblance to how it looked at all before the flood. So, the Middle East is supposed to represent the Garden of Eden, the origin of the location of the Ark when it landed. I'm not necessarily convinced. I mean, they named the Euphrates and Tigris and all that. I think they based the names of these rivers based on the remembrances of what the rivers used to be like, not necessarily an actual location.
And doesn't the Bible refer to the continents before the earth was divided or something like that?
In the days of Peleg, the earth was divided.
Yeah, something like that.
That's the only statement. It's a kind of a brief statement, and they don't talk about it anymore. And so you kind of make what you want out of it. But to me, it sounds like a catastrophe.
Well, there appear to be many oil fields in the ocean, so that would mean that there has been life in that area, wouldn't it?
There are some sedimentary layers in the ocean, but they're usually more close to the continents. Because the problem is that especially in the mid-Atlantic ridge, the continents have indeed moved apart from each other and built that ridge. And so when they moved apart from each other, the volcanic activity produced the crust there, and there's really no sedimentary layers there. And which is kind of interesting to me, because if let's say you hit something really quick with a lot of energy and it rapidly splits apart, and these sheets start crashing into each other and warping, it's kind of like, I imagine it like two cars crashing into each other in a collision. When you crash in very rapidly, at first the mountains will go quickly, the valleys and mountains will go quickly because there's a lot of energy released. But after the cars crash into each other for a while, they slow down exponentially. And now, yes, we're still moving apart. The ocean ridge is still moving apart a couple centimeters a year. But to me, it's like at the tail end of the crash. We're dissipating a lot of energy here, and the majority of the energy is gone, and have already built our mountains and ocean trenches and whatnot. And the oil found in the oceans is usually like in the Gulf of Mexico, not in the middle of the Atlantic. Yes.
We can remember that in Genesis it talks about as God created that there were a separation of two bands of water. One band of water went out under the earth, and a band of water went over the earth. And so therefore, with that band of water that went over the earth, it could have easily, because that came down, could have easily created our oceans.
Yeah, that's true, but there's also a whole lot of water deposited in the rocks themselves.
Yeah,
if you squeeze the rocks just of the entire Asian continent alone, it would bury the whole earth in water up to, several thousand years. Just the water embedded in the rock alone. You put a lot of pressure on that all of a sudden, you're going to have plenty of water to bury all the continents.
Sure.
Especially if there's no Mount Everest or any huge Himalayan ranges. Also, the interesting thing about the water, I don't talk about the water above the earth very much, because I think it's a lot of speculation about that. But it's interesting to speculate sometimes. Because, pterodactyls, they got this huge wingspan and a pretty high body weight. In current atmospheric pressure, they couldn't fly. And it turns out that you need about 2 or 3 times the atmospheric pressure of today for pterodactyls to actually fly. And also the Bible talks about running and not being weary. All the way talks about people never getting tired before the flood. They could work all day long, run all day long, they never got tired. It seems almost to me that it's suggestive of hyperbaric conditions. That you heal really fast when you're in a hyperbaric chamber. It's used for hospitals today to help people heal from diabetic ulcers and things like that. I think the whole world perhaps was a giant hyperbaric chamber. So, there seems to be some, the plants were bigger then, animals were bigger, everything was bigger and better then. And there's been some recent experiments also to that effect today. Yes, sir.
What about ice core? Do you hear people talking about counting hundreds of thousands of years of layers of ice cores?
Yeah, I have a whole lecture on ice core dating. I almost thought about presenting it here. There's there's so many problems with ice core dating, and I can talk to you privately probably. In brief, though, I can give you kind of a summary. There can be more than one ice layer per year. Also, when you in hot and cold spells, you can create artificial layers, because let's say it gets warm one day, well, the snow, that's called the snowy firn, it gets a little crispy on top. And then when it's buried by the next snowstorm, you see a layer there that still preserved that crispiness, where it was a little bit of melt, and it looks like a layer. And so visual counting is not reliable, and so what they resort to then is chemical analysis, usually based on dust layers or acid layers, where in the summer it's supposed to be more acidic because you evaporate certain isotopes from the ocean and deposit it summer, winter, summer, winter. The problem is that these things move. The acid spikes and the sodium spikes and all those things move through the ice and the snowy firn. They percolate, and they get trapped on these previous layers and at different concentrations. And so they create artificial boundaries, artificial layers that have the appearance of layers. But when you actually measure them in real time, the resolution drops from 1 layer per year down to about 10 layers per year. And that's in real-time studies that have been done on Baffin Island and other areas north of the Arctic Circle. And so now let's say you have 100,000 years. If your resolution is down to 10 layers per year, what's the best you can say about the age of those 100,000 layers? The best you can say is that at best they represent 10,000 layers that you can be sure of. 10,000 years that you can be sure of. And, you want to get a little bit more shaky as you go lower, the layers become microscopic almost. They get thin and stretched out. So I can talk to more people afterward. I don't want to keep people too long. Sorry, my wife is tapping on the watch. So I will let you all go. I appreciate you all coming today. So hopefully we'll see you all tomorrow.